And we're going to start a special topic, chemistry and industry and technology. Okay, and there are a bunch of sections in this section, subsections, I guess you would call them. So let's get started. Let's talk about metals and metal ores. We're going to start with iron, steel, and aluminum specifically. Okay. Some metals occur in nature as the pure element, and those would be gold and silver. And if you think about gold mining, silver mining, hopefully you can remember that those two can exist in nature. They are fairly unreactive compared to the other metals. Most metals, the more reactive ones, occur as ores. That means they're combined with other elements. Typically, these would be oxides, sulfides, and carbonates. And then you have other things mixed in there because ore basically is in the dirt, right? In order to use these different metals, and the use of metals is in our society is just huge. Building buildings, cookware, silverware, braces on teeth. I mean, it's everywhere. All right. So in order to use it, you've got to get the metal separated from the impurities, the oxygen, sulfur, and carbonates. So most often this is done with some reduction. Okay, remember your redox reactions. This unit will serve as kind of a mini review for redox as well. Okay, so we reduce the metal and then we remove the impurities. And then how we extract that metal, how we separate out those impurities does depend on how active the metal is. And if you recall, there is an activity series. In the order of decreasing reactivity, potassium, one of the most reactive, and going all the way down to silver and gold, which can be found pure. From potassium, sodium, calcium, magnesium, aluminum, these are all reduced through electrolysis. Zinc, iron, lead reduction can be accomplished through roasting with carbon, and then copper is decomposed by heat and then extracted through electrolysis to maximize the purity. And you do kind of have to know where these different metals fit in. That is something that the IB expects you to know. All right, so let's focus on iron and steel. Iron, an iron ore, is dug up from the ground in deposits. These were formed at least 1.5 billion years ago. Iron oxides exist as magnetite, hematite, and others that make up iron, and you do have to kind of know the specific names for the iron oxides. The iron oxides in particular, this does not actually have to be capitalized, are put in a blast furnace to make iron, and we're going to look at the blast furnace and how that works in just a moment. Most of the iron mined comes from Australia and Brazil. Oh, one other thing to add here. There is another ore that is pyrite. This one is typically not refined because it contains sulfur, and it would produce SO2, sulfur dioxide, which causes acid rain, and that is no good. Okay, so it's a pollutant, so they try to stay away from that, or leaning towards the magnetite and the hematite, I'm sorry. Okay, so deposits in the earth come from blue-green algae releasing oxygen. And then the irons form when the algae went through cycles of blooms and busts. And these cycles, through the billions of years, contribute to the formation of magnetite with the formula Fe2O3, or iron 3 oxide, and hematite, which is iron, well, it's Fe3O4. All right, and then again, iron sulfides, the pyrite, typically not used because you will form sulfur oxides and acid rain problems, detrimental to the environment. All right, so looking at a graphic organizer, we've got iron ores, the three types: Hematite and magnetite, again, iron extracted in the blast furnace. Be careful of this spelling. I think an extra A got in there. Iron pyrite, again, roasted in air, forms oxides, and that SO2, which is bad news for our environment. This is a nice way to kind of organize those thoughts. All right, so we're going to talk about the function of a blast furnace. And this is used to purify iron oxides in iron, and really doing what its name implies. There involves the addition of iron ore, coke, and limestone. Limestone is just a common name for calcium carbonate. Hot air is blown in from the bottom. The ore is added at the top of the blast furnace as pellets, and what that does is basically just increase the surface area, which increases the reaction rate. And then the iron ore is put in the furnace and heated up, and there's a series of chemical reactions that removes the oxygen and transforms it into pure iron. Right, and here is a picture of a blast furnace. You can see that it is fairly large. If this is a 2 or 3 story building and this is the blast furnace in the back, it's kind of big. All right, hot air comes in from the bottom, okay, and goes through the top. Here is the coke, limestone, iron ore getting basically crushed up into pellets up a conveyor belt and gets dropped in the top. This is really probably just a distribution bar just to make sure that it breaks up and flows evenly down the blast furnace. All right, and then hot air ore goes down, reactions occurring in here, getting your iron at the bottom. This is looking at a schematic. You should be able to highlight the main parts of a blast furnace. Right, your ore, limestone, and coke coming in here. Waste gases going out the top. These are used. Excuse me. These are used to heat some of the air that's coming in, so that you do regain some of the energy lost. You make a slag that is kind of a waste material but is used, and then your molten iron at the bottom. It is all lined with fire clay bricks for installation. Look at the reactions that are going on in this blast furnace. We have carbon with oxygen producing carbon dioxide, and we can see that that is exothermic. This heat of reaction causes an increase in temperature, causes the reaction of the limestone being calcium carbonate. Calcium carbonate will decompose into a calcium oxide and carbon dioxide. That carbon dioxide then reacts with more hot coke, the carbon, to produce carbon monoxide. Then this carbon monoxide is the reducing agent for the formation of iron. That redox reaction looks like this. We've got the iron oxide with the carbon monoxide going to carbon dioxide and another iron oxide. That iron oxide reacting again with the carbon monoxide to form yet another iron oxide being reduced. That iron oxide reacting with the carbon monoxide to produce carbon dioxide, and finally just iron. So this entire mechanism can be written together with this equation. Notice that the iron is in its molten form. It's pretty hot at the base of that blast furnace. So the iron produced sinks to the bottom of that furnace where the temperature is high enough to keep it molten. That iron is run out of the bottom and it's poured into molds called pigs. And it produces what they call pig iron or cast iron. The reason why this is called pigs is the original molds kind of look like little piglets feeding on their mom. So it's like little sections all connected with a channel in the middle. Kind of like if this is the channel of the hot iron, you would have these pigs. Oh, goodness. Yeah, my drawing, Okay. And then this is where the hot iron comes in here and fills up this mold. That is really not a very good drawing, but I'm hoping you get the idea. All right, slag. Slag is that part that sits right above, here, we'll go back real quick to the slag is this section here, this material that sits right above the pure molten iron. Okay, so that's the slag. The main impurities in ore, again, are aluminum oxides and silicon dioxides. These are important to remember what the major impurities are. Now, this high temperature, again, this limestone decomposes to calcium oxide and carbon dioxide. That calcium oxide then reacts with these impurities in the iron, the silicon dioxide and the aluminum oxides, and they form these components. This together is what's called the slag. That slag is used to make cement and roads, right? And again, the gases from the top of the furnace are recycled back to heat the incoming air. Okay, so even though we've got the iron now purified from ore, it can once again be purified. Iron produced from the blast furnace contains about 4% carbon. This makes it fairly brittle, and it's limited in its use. It's actually called cast iron, and it's not very malleable, right? So most of the iron got from or made from the blast furnace is made into steel. And steel is widely used because it's stronger than just the iron, and the strength is due to the lack of impurities. All right, when you say steel, there's a whole broad category that steel falls into, and it depends on what they add back into it to impart some properties to that iron. You can have stainless steel, you can have 504 steel, you can have 314, 306. There's all different grades, and it all is just pertaining to what they add back into the steel. All right, so uses of steel, mainly used as a commercial product in cruise ship hulls due to its resistance to changes in temperature and pressure, cooking utensils, and infrastructure material to build buildings and bridges. All right, so iron to steel. Steel producing plants use the basic oxygen conversion method over the open, assuming that's supposed to be hearth, method due to the increased speed. So using this basic oxygen conversion method is going to be faster. Okay, basic oxygen conversion, short name BOP. Okay. High purity oxygen blows through the impure iron, which lowers levels of carbon, silica, manganese, and phosphorus. Fluxes, these are cleaning agents. They're used to aid in reducing the phosphorus and sulfur levels. And then you add alloying agents such as nickel and chromium, and again to impart different properties to the steel. Okay, and this is what a basic oxygen converter looks like. You've got the molten iron and steel scrap at the bottom. These impurities tend to go form a slag at the top of here, of the molten iron. You've got a water-cooled oxygen lance, and that's probably just to keep it from melting. This converter is where you're going to pour out the material, see, tilted for pouring. And you've got a fume hood with waste gases. Okay, here is the entire setup. You would feed scrap into this furnace. This is probably a liquid steel ladle, meaning this is going to be when this is tilted, the molten material goes into here, and then you can bring it wherever. Right, so what happens in this BOP? Removal of carbon is carbon dioxide, removes sulfur as sulfur dioxide, and oxides of silicon and phosphorus are also formed. Okay. Those phosphorus and silicon oxides react with calcium oxide to form more slag. stop there. We'll pick up